students. Uh, Here this is Dr. N.G. Praveena, working as Associate Professor in the Department of EC at R.M.K. College of Engineering and Technology. In this presentation, I would like to discuss the basic concepts of differential pulse code modulation, Dpcm transmitter and receiver, followed by SNR derivation. Why we go for Dpcm? We have started the digital modulation techniques with so many modulations. PCM is the base of your other modulation technique. The PCM, the signals are sampled at a rate which is slightly higher than the request rate. This is nothing but your sampling theorem. Hope everybody knows it. And the resulting sampled signal, when you find, it will experience a high correlation between the adjacent samples. What is meant by high correlation? It means that the signal will not change rapidly from one sample to the next. So when you compare the signals from one sample to the adjacent samples, it will not change rapidly. It will change very slowly. The signal variation will be very, very less. It means that the variance of the signal is very, very smaller. When these samples are encoded in PCM, obviously the resulting encoded signal will contain redundant information. What is meant by redundant? It's nothing but duplications of bits. So when we remove this redundancy before encoding, we can obtain a more efficient coded signal. Here, what we are going to do is, we are going to apply a simple concept. We should know the past behavior of the signal. If we know the past behavior of the signal, we can easily predict about its future values. This is nothing but the principle of your Dpcm, which is nothing but prediction concept. So we are going to apply prediction concept in Dpcm to find out the future values from the knowledge of the past samples. Assume we have a baseband signal which is represented by x of t, which follows an request rate. Hence it is sampled at a rate of fs, where fs is equal to 1 by ts. We are going to take the samples that is represented by x of nts, where n is nothing but an integer values. We are going to predict the future values of the signal x of t. Here it is a simple waveform which is representing the Dpcm working and application. Here there are various samples we are taking at the various intervals. Here one is Ts, 2 Ts, 3 Ts, 4 Ts, 5 Ts, 6 Ts and goes on. In Ts, the samples are taken and it is encoded with the corresponding levels 0, 1, 0. And the sample at 2 Ts has been encoded as 100, and at 3 Ts it is sampled as 101, and at 4 Ts it is encoded as 110, and in 5 Ts it is same 110, and in 6 Ts it is again 110, and in 7 Ts you can see the encoded data is 101, and in 8 Ts it is again 101, and in 9 Ts it is again 101, and in 10 Ts it is 100. So when you look at this waveform, it is so clear that the samples at 4 Ts, the samples at 4 Ts and 5 Ts and 6 Ts have same encoded data, that is nothing but 110. Instead of transmitting 3 samples which carries the same information, in order to avoid redundancy, we are going to transmit only one sample. We are going to transmit 110. Instead of transmitting thrice, we are going to transmit 110 only. Similarly, look at the samples at 7 Ts, 8 Ts and 9 Ts. All the 3 samples are encoded with the same bits 101. Here, instead of transmitting 3 times, we are going to avoid the redundancy. I am going to transmit only one time 101. Here similarly 110. So this is the concept of your Dpcm. So here the sample at 5Ts has been predicted with the help of 4Ts. Similarly, the sample at 6Ts has been predicted with the help of 5Ts. And similarly, the sample at 8Ts is predicted with the help of 7Ts, and 9Ts is predicted with the help of 8Ts. So this works under a concept of prediction. So this works under a concept of what? Prediction. Now we are going to discuss about the Dpcm transmitter. Here this is your transmitter block diagram. I have a signal, it's nothing but Mn. I am going to represent the signal as Mn. This is applied to a comparator. This block is called as a comparator block. The comparator, as the word implies, it is going to compare the difference between my Mn and Mn cap. The difference is nothing but En. So I can write down the mathematically En is equal to Mn minus Mn cap. So what is Mn? Mn is nothing but my sampled version of the message signal, whereas Mn cap is nothing but my predicted signal, which is obtained from the output. Here the En is nothing but a error signal, which is nothing but the difference between my sampled signal and the predicted signal. This En is applied to a quantizer. The quantizer will quantize the value of En, sample En, and it will produce the quantized output, which is represented by Eqn, which is mathematically, I can write down Eqn is equal to quantization of En, right? When we do quantization, obviously we will get an error. So I am writing this as a quantization error that I can write down as Qn. Right? What is Qn here? Qn stands for quantization error. You are applying this Eqn is nothing but my error comparator output plus my quantization output. When you look at the diagram, this Eqn is given to an adder, right? Is given to an adder. The adder output is taken as Mqn, represented by Mqn. It is applied to a linear predictor. The output of the linear predictor has been represented as Mn cap. So mathematically I can write down what is Mqn. Mqn can be written as Eqn plus Mn cap. So what is Mn cap? Mn cap is the predicted signal of Mqn and Eqn is the quantized output. This Mqn has been fed to a comparator, has been given to a linear predictor, then the output of the linear predictor is Mn cap, is finally given to a comparator. So when I do like this, okay, when I do this, what happens? Right, the output signal has been quantized, right? Finally my Eqn is given to an encoder. The encoder will encode the signal Eqn, thereby it produces my encoded signal for each samples Mqn. With a simple illustration, we are going to explain the sequences of this with the data. I am taking a samples of various instances. This is my sample N. Mn is nothing but my signal. Mn cap, what is Mn cap? It is nothing but my comparator signal, and En is my comparator signal. Eqn is nothing but comparator output. Mqn is nothing but the input of your linear predictor. Initially, I am taking the sample at 0. Assume my Mn is 2.1. I am taking Mn cap as 0. Initially, I am taking Mn cap as 0. Right? So En is nothing but Mn minus Mn cap. So it is the difference between the two signals. So En is nothing but Mn, En is nothing but Mn minus Mn cap. So 2.1 minus 0 is 2.1. This is applied to a quantizer. The quantizer will round off to its nearest integer. So 2.1 is round off to the nearest integer, that is 2. You are taking a feedback. Once again, this is your Mqn2. Right? Now take the second sample at n equal to 1. Here the sample value is 2.2. 2.2. Here Mn cap is nothing but the previous value of Mqn will become Mn cap. So, this 2 will be taken as an Mn cap. Now, what is En? Mn minus Mn cap, 2.2 minus 2 is nothing but 0.2. When 0.2 is quantized to the nearest integer, it is obviously 0, right. So, now this Mqn is nothing but, how Mqn has been taken? You have to add Mn cap and Eqn, that is nothing but 2. Like this, the sequences has been produced for all the samples. Here we are going to discuss about the Dpcm receiver. How the signals are reconstructed with the help of this block. I have a decoder block. I am applying a noisy version of Dpcm encoded signal which is given as an input to a decoder. The decoder has been given to a summer block, where summer block receives an input from the linear predictor 2. The output is your Dpcm decoded output. The decoder reconstructs the quantized error signal from the incoming noisy version of Dpcm. The prediction filter output and the quantized error signal are summed up, right. The prediction filter output and the quantized error signal are summed up, which gives the quantized version of my original signal, that is nothing but U of Ts. In the absence of channel noise, the encoded signal at the receiver input, when we do not have noise in the system, ideally we can assume this situation. When there is no noise, the encoded signal at the receiver input is identical to the encoded signal at the transmitter output. We are going to discuss about the signal to noise ratio of Dpcm. What is signal to noise ratio? So, SNR we are going to find out. SNR can be written as signal variance divided by noise variance. Noise is nothing but my quantization noise. Here mathematically I am going to rewrite this equation by multiplying and dividing by sigma E square. So, sigma E square divided by sigma Q square. Here the sigma x square by sigma E square, I can write this as Gp, whereas it is represented by prediction gain, and sigma E square by sigma Q square is nothing but SNR of my prediction filter. So, what is Gp mathematically from this? It is nothing but sigma x square by sigma E square. So, this is your prediction gain which is obtained by the prediction filter, and SNRP, signal to noise ratio of the predictor, is nothing but sigma E square divided by sigma Q square. So, for a given baseband signal, the variance sigma x square is always fixed. It is not a variable quantity, it is a fixed quantity. Hence, Gp can be maximized by minimizing the variance of the noise. In this way, we can improve the SNR of your Dpcm method. Thank you all.